Okay. All right, we're going. So welcome in this morning. Today's Thursday. So the plan today is to talk about oxidation reduction reactions or reduction oxidation reactions. And we're gonna, if there's enough time, we'll talk a little bit about concentration of solutions as well. But the focus will be on oxidation reduction, which is section 4.4. Okay, oxidation reduction. Okay, any questions? Any questions on acid-base chemistry or precipitation chemistry before we get started on the oxidation reduction? Okay, all right, so let's talk about, we call it redox chemistry typically. So redox chemistry, I'll write a little abbreviation here. Redox. It's a very important type of set of chemical reactions, which are quite diverse. Many different types of redox chemistry are all driven by the following. The idea that a reducing agent transfers one or more electrons to an oxidizing agent. Okay, oxidizing agent, reducing agent. So those are reactants. The term agent is another word for reactant. So we could very well call this the reducing reactant transferring electrons to the oxidizing reactant. Okay, so essentially what happens is one either atom or molecule or ion, depending on what it is, will transfer electrons to another atom, ion, or molecule. So I'm going to write the electron as an E, a lowercase e for electron, and then we'll put the negative there to indicate that it's negatively charged. You know, there's actually an opposite particle. This is called an electron. In nature, there's actually an opposite particle. It's an electron with a positive charge, and it's called a positron. And this is observed in nuclear processes, but not in redox chemistry. Okay, so we'll only deal with the electron. So here's what we would do. I would say that if you look at the picture that I've drawn here, the diagram, see how the electron is moving from one substance to another? The one that it's coming from is called the reducing agent. And the one that it's going to is called the oxidizing agent. Okay. An example of that, just to show you a little of the chemistry, an example of that would be if we had a silver ion. This is silver, argentinium, which is positively charged. Now, this would be occurring in water, so I'm not going to show the water molecules. And if we had next to that, let's say a lithium atom. Well, I wrote that L pretty big. We don't need to have such a large L. A lithium atom. Okay. The lithium atom would transfer an electron to the silver ion. Okay, so an electron would move from the lithium to the silver ion, right? And so this would be the reducing agent. You can think of the reducing agent as the source of the electrons. It's where the electron is coming from. And then this would be the oxidizing agent. Okay, This is the where the electrons go. Now, interestingly, what would happen then is if the lithium atom transferred an electron to the silver ion would now be a silver atom, right? This is now a silver atom. Why? Because it was positively charged. It's an ion. But it's now gained an electron, which is negatively charged. So that negative charge of the electron will cancel the positive charge of the ion. And so now it's a neutral silver atom. If an atom is neutral, we just call it an atom. If it has a charge, we call it an ion, right? So likewise, or counter to that, the lithium, because it's transferring an electron, so it's losing an electron, right? And what would happen there is now the lithium would have a positive charge because it lost a negative charge. So if something starts off with neutral charge, meaning no charge, and then it loses a negative charge, it's now positive. So this would be called a lithium ion. And in chemical terms, what we would do is we would represent this without the little circles around them, right? So we would just write Ag plus Li. Those are the reagents, right? The agents. You could call them reactants, you could call them agents, you could call them reagents. All three mean the same thing. And then on the product side, we would have a silver atom, and we would have a lithium ion, okay? So that is an example of a redox reaction, right? The transfer of electrons occurring, in this particular case, the lithium atom is transferring an electron to the silver ion. And it doesn't have to just be one electron. There are reactants where, reagents where 2 electrons might get transferred, or even 3 electrons, okay? Generally not more than 3, but it's even possible to have more than 3, okay? So that's a redox chemistry. So what's left out of that then is really just kind of focusing on some of the notation that we work with, and then doing some of the equation writing and assigning oxidation numbers. So I'm going to begin. The first ALEKS problem here is what we call assigning oxidation numbers. They're not called reducing numbers. We could come up with a system called reduction numbers, but oxidation numbers is the term that we use. So in this particular problem, what they do is they give you the formula of several substances, and then they color one element from each substance. So I'm not going to color them, I'm just going to underline them. Okay. And then what they want you to do is to find what's called the oxidation state. And you can use the term oxidation state, or you can use the term oxidation number. We'll use both terms. So you can either say state or number, it doesn't really matter, okay? So what you're going to do is you're just going to say, hey, what is the oxidation state of the element that's underlined? So I'll write a little number over here, okay? And here's how we go about doing this. This is essentially determining, if you want to think of it this way, it's sort of like determining what the charge of the atom is. What is the charge of the atom in that substance, okay? So for example, the third one here, potassium, you know what the charge is. The charge is +1, right? It's K plus, so the charge is +1. In a sense, the oxidation number is kind of the same thing. It's kind of the charge. Now, there are physical reasons why it's not exactly the same, but for our purposes, it's useful to think of it in those terms, because then you can do the calculations. So in a sense, think of it as the charge. And the idea is essentially this. Imagine this copper oxide. We can imagine the copper oxide as being an ionic compound where the copper has a charge of +2, right? And the oxygen has a charge of -2. And now CuO is what we call the empirical formula. That means that's the lowest ratio, the lowest whole number ratio of the atoms in that compound. But essentially, this is an ionic compound, right? It's got a metal with a nonmetal, so it's probably a copper-2 ion combined with an oxygen -2. And if that's the case, if the charge of the atom that we're interested in this case it's copper, if it's an ionic compound, whatever the charge of that ion is, it's the same thing as the oxidation number. So we would just write the oxidation number. Now be careful, when we write charges, we write the number and then the sign, 2 plus, 2 minus. But in terms of oxidation numbers, you actually write the sign first. And that's a way of telling people that it's the oxidation number and not the charge. But very often they're the same thing. So I'm just going to write +2 for the copper. The copper here is +2 because I figured out, well, how did I know that? I remembered that oxygen is in group 6A. And I remembered that if you're in group 6A, the charge of the ion is -2, right? And so then I said, wait a minute, it's neutral. So that means whatever the negative charge is, you have to have the same amount of positive charge. So if the negative charge is -2, that meant that the positive charge has to be +2, right? So then that tells me the copper is +2. Okay. Now that works pretty well for ionic compounds. So if you have a metal with a nonmetal, that works well. Just figure out what the charge of the ion is. So over like the third one, right? This is not even a compound, right? It's just an ion. It's just an ion. So if it's just an ion and it's one atom, then whatever the charge of that ion is the oxidation state. It is the oxidation number. So since it's plus, the oxidation number would also be +1. There you go. So there's the second one. So if it's an ionic compound, okay, if it's an ionic compound, the charge of the ion is equal to the charge of, is equal to the oxidation state. And you can see that those rules that we learned back in chapter 3 and 2 and 1, they're actually covered all the way back to chapter 2. They're essential, knowing which group you're in. So if you're in group 1, it's your +1. If you're in group 2, you're in +2. If you're in group 6A, you're +-2, and so forth and so on. And then if you have a monatomic ion, remember, monatomic just means one atom. Okay, so that would be here. That's a monatomic ion. Then in that particular case, the charge of the ion is equal to the oxidation state. Okay, so if I were to give you another one, if I said, hey, here's copper +2, what's the oxidation state of that copper? You'd say, oh, that's a monatomic ion. The charge is +2 or 2+. So that means the oxidation state has got to be +2. It's very simple. If I said, hey, here's N3-, that'd be simple too. You just say, oh, that's a monatomic ion, so it's got a charge of -3. So the oxidation state is -3. Okay, so that's pretty straightforward. Ionic compounds and monatomic ions. The issue that gets more complicated is how do you deal with molecular compounds, molecular substances? So these two here that I'm circling are not ionic, right? Hydrogen and oxygen are both nonmetals. So that's not an ionic compound, that's a molecular compound. The same is true for the carbon tetrafluoride, CF4. Carbon is a nonmetal, fluorine is a nonmetal. If both elements are nonmetals, it's not an ionic compound, with a few exceptions. So how do we deal with that? Well, we have what we would call kind of rules about oxidation numbers. And so here's our rules. And this is mainly for dealing with molecular substances. And the way you deal with that is there's sort of a hierarchy of the most important rule followed by the less important rule, less, 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 less. So it's a hierarchy. So the first one is that in a molecular compound or a molecular ion, fluorine is equal to -1. Just by definition, we just call it -1. Now that's not so hard to remember because if you remember, the halogens are in group 7A and they're all -1 anyways, right? So for that particular case, that works out pretty nicely. You just put fluorine as -1, okay? So the second rule is that hydrogen is +1. And again, that's not so bad either because hydrogen is in group 1A and we already know about the hydrogen ion from acids, so +1 is not that unusual. The third one is that oxygen is -2. But I must tell you right now, I have to warn you that for rule 2 and rule 3, there's a few there are exceptions. And so the exception here is that, let me do the hydrogen. I don't want to spend a long time on the exceptions because they're exceptions. They're not what you normally see, but they are important. So the exception, the first one is for hydrogen. If you have a metal and it's bonded to a hydrogen, so if you see the hydrogen in this order, a metal then hydrogen, which you're not going to see very often, this is called a hydride. So a metal with hydrogen is called a hydride. And if it is a hydrogen, then the hydrogen is actually negatively charged. This actually exists. It actually exists in nature. And so we would say the oxidation number for hydrogen is -1. Okay, so you're not going to see that very often. Most of the time, hydrogen is +1. In fact, 99% of the time, hydrogen is +1. However, because hydrogen can exist as -1 if it's combined with a metal, that ends up making it a very powerful reactant. It gives it properties that are very useful in the laboratory. You can get it to do certain things that are hard to get other things to do. And so for that reason, chemists do produce, the industries do produce hydrides and they sell them. They're not very stable, they're pretty reactive, and they do break down, but they do exist. So if you see a metal, so it could be potassium, it could be lithium, it could be calcium, it could be sodium. Generally, it's the first two columns of metals. With a hydrogen, then in that case, you recognize that's a hydride. That's the exception to hydrogen. But again, almost all the time, hydrogen is +1. The exception for oxygen is somewhat similar, but a little different. The exception for oxygen is that if you have the following formula, not H2O, but H2O2, or Na2O2. Take a look at the similarity in those two compounds. See how you have 2 hydrogens and 2 oxygens, or 2 sodiums and 2 oxygens. So if you have 2 hydrogens with 2 oxygens, that's called hydrogen peroxide. That's the stuff that you can buy in the drugstore over the counter. You just go in the shelves and buy it. You can use it for cleaning. You can use it for disinfecting. Some people even use it. They add it to brush their teeth, to kill bacteria and stuff like that. If you have an injury, you can use it to kill the bacteria in the tissue. That's called hydrogen peroxide. It's a peroxide. And the same is true if you have a metal. So just like with the hydrides, if you have one of these metals like sodium or lithium, and it follows the format 2 of them with 2 oxygens, that is called a peroxide. And in that case, each oxygen is actually -1. Again, that's why peroxide is useful for killing bacteria. The peroxide is very reactive because of that strange -1. Oxygen is almost always -2. And so in this case, the oxidation number of oxygen is -1. Each one is -1. So in the peroxide, each one is -1, okay? And those are the kind of the primary exceptions. And there's not very many of them, right? So just the hydride, if it's a metal with hydrogen, then it's -1 instead of +1. And if you've got 2 of the metals or 2 of the hydrogens with 2 of the oxygens, in that case, the oxygens are a peroxide and they form a -1 charge. So the oxidation state would be -1. Okay, so those are exceptions. In a sense, that kind of gets you there. You're pretty much set for almost all of the compounds. So fluorine is -1, hydrogen is +1, oxygen is -2, a couple of exceptions. If you have an ionic compound, just figure out what the charges of the ions are, like we've talked about before. Those will be equal to the oxidation state. And then if it's a monatomic ion, whatever the charge of that ion is the charge of the, or is the oxidation state as well, okay? So that gives us enough information to finish the last two. Water's an easy one, here's why. It's not H2O2, it's just H2O, right? So there's no O2. So in that case, we're just gonna follow these rules. Hydrogen is +1 and oxygen is -2. Remember, you write the charge and then the number if you're doing oxidation states, right? That's all we had to do there. Just look it up in that little table there. So just memorize these three with the two exceptions. Carbon tetrafluoride. Okay, well, we don't have any rules for carbon, but we do have one for fluorine, right? Fluorine's the most important, not the most important, but the highest on our hierarchy. When in doubt, fluorine is -1, okay? So what you do with this one is you say, okay, well, I don't know what carbon is. So I'm just gonna write carbon, C. And then how many fluorines are there? There's 4 of them. So I'm gonna write +4, and each fluorine is -1. And then you look at the formula. The formula doesn't have any charge. So that means all the oxidation states add up to 0. So whatever that charge is, in this case it's 0, the oxidation numbers have to add. So these are the oxidation states. They have to add up to the charge. So in that case, they have to add up to 0. And then what you do is you just solve for C. You just figure out what C is based on that algebraically. So C plus 4 times -1 is equal to C plus -4, right? 4 times -1 is -4. And then you add 4 to both sides, and you get +4. And there you go. The oxidation state of carbon is +4. Okay? Relatively simple.
Wait, I have a question.
Yeah, go ahead.
You said they have to add up to 0 because they have to cancel each other out, right?
So they have to add up to 0 because a molecule or a compound has 0 charge. So the oxidation states, they have to add up to whatever the charge of the species is. So let's say that, so for example, this one, see how this one's -3? The nitrogen is -3. So they can be different numbers, but they have to add up to whatever the whole thing is. So in this case, see how they added up to 0 again? +2 -2? Because they had to add up to 0 because that's a compound.
Okay.
Let me show you one that will make that kind of a little, so you can kind of see the difference. Sometimes you need to see a different example for it to make sense why it's that way. I'm going to show you the hydroxide ion. That's one we're familiar with, right? So for the
Wait, so the
ahead.
oxidation numbers, how do you know which one to put, the carbon or the fluorine?
Oh, they underlined the carbon. So whichever one got underlined, whichever one they're referring to. So I actually underline them, but in the problem on Alex, they make it red. They color it in red. So they say, you know, assign the oxidation state to the element that's in red, right? So I underline them just to assume. Okay. So let's take the hydroxide ion, for example. You know, based on our rules, oxygen is -2, right? So oxygen is -2. Based on our rules, hydrogen is +1. if you add those together, look what you get. You get -1, right? And that is the charge, right? So if you add the oxidation numbers or oxidation states, they're going to equal the charge of the ion. So what happens in CF4 and what happens in H2O and what happens in CuO, those are all compounds. Those compounds have no overall charge. So even though the little atoms have charges, overall they have to add up to 0. So that's why with the carbon tetrafluoride, we wanted it to add up to 0. Okay. Let me show you another example. So here's let's do K. This one's a harder one. I'm going to show you this one, but I'm not going to do this one first. I'll do a simpler one first. Let's do MnO4. Let's do CrO2. That one's a little easier. Let's do CR2. This one's a trickier one again, but I think it's good to do a couple harder ones. That one right there. And let's do BiO3 minus. You're going to notice when you do these problems, there's a lot of oxygens and hydrogens. Those are the two elements that show up a lot. And the reality is that most of the compounds we deal with have oxygen or hydrogen or both of them in. And they're very plentiful elements in nature. So let's take a look at these. I'm going to do the KMNO4 last because that one's the most complicated one. The easier of the two are this one and this one. And here's why. If you take a look at the CrO2, that's a compound, right? It's got a metal, a non-metal, it's an ionic compound, and it's neutral because it's a compound. Compounds are neutral by definition. If you look at the third one, that's not a compound because it has a charge. This is a polyatomic ion. If you look at the fourth one, that's not a compound. It's a polyatomic ion because it has a charge. And so it's the case, this is a compound, right? How do I know it's a compound? It's got more than one element in it, and it doesn't have any charge given. That's what a compound is. So two of them are compounds, two of them are polyatomic ions. Here, when you add all the oxidation states, they got to equal 0. That's what a compound is. All the oxidation states have to add up to 0. So the same would be true with this one. If you add up all the oxidation states, they also have to equal 0. But for these two, they're not compounds, they're polyatomic ions. So when you add the oxidation states here, they have to equal the -2. They have to add up to the charge there. Because again, in a sense, the oxidation states, in a sense, are measuring what the charges are. We're thinking of each atom as having a charge. And then the same thing here. If you add all the oxidation states, there's your charge. So it's got to add up to -1. Okay. And then it doesn't matter how complicated the formula is. That's just sort of the way it works, right? If it's a compound, it's all got to add up to 0. So H2O, CF4, they had to add up to 0. Now let's take a look at, I think, let's do the CrO2. That's the easiest one. Okay, again, there's not very many rules that I gave you. You will find lists online that have more rules, and those can be useful, but really it's just the ones I gave you. So CrO2, there's a rule about oxygen, which is that oxygen is -2. So here's the way I'm going to do this. I'm going to identify it as a compound, so that means they have to add up to 0. So I'll write the 0 on the left side. I'll just say 0 has got to equal whatever the chromium is. Again, we don't have a rule for chromium, so we don't know what it is, right? But we do have a rule for oxygen. And look at how many oxygens there are. There's 2. So I'm going to write plus 2 times -2, right? That's your 2 oxygens, and that's your chromium, CrO2. And because it's neutral, it's got to add up to 0. And then what you do is you just solve for chromium. Okay, if you were asked what is the oxidation state of chromium, then you would figure it out. For this type of problem, they're not going to ask you for the oxidation state of oxygen because you just, you just remember that. You remember it's -2. So let's see how we go about this. 0 is equal to chromium plus 2 times -2. So that means 0 is equal to chromium -4, right? 2 times -2. And then you add 4 to both sides. So remember, when you're adding 4 to both sides to get 0 on this side so that you only have chromium, right? So +4 equals chromium. So the oxidation state of chromium would be +4, if that were the question, okay? Let's take a look at the next easiest one, which is the BiO3. This is called Bismuth Eight. Okay, you have one bismuth, so I'm just going to write Bi. Why am I writing it? Because I know there's no rule for bismuth. We only have a rule for oxygen, hydrogen, and fluorine. But we also have 3 oxygens, and we do have a rule for oxygens. So 3 times -2, right? Bismuth plus 3 oxygens. And now the charge is -1. So now it's equal to -1. Okay. If the formula were just BiO3, then you would add up to 0. And so bismuth, 3 times -2 is -6, so -6. You add 6 to both sides. So that'll give you 0 here, and it'll give you bismuth. And then that's going to be -1 plus 6 is +5. And so for this particular one, we would say that the bismuth is +5. Okay. Let's see.
Wait, where did you get the -1?
Right here.
Oh, okay, fine.
Yeah, there's your charge. It's got to equal the charge. So the sum of the oxidation states has to equal the charge. Okay. And if you don't see a charge there, then it must be 0. Let's try the KMnO4 now. This one's more complicated because it has 3 elements, right? So here's how you deal with it. The way you deal with this is you recognize that you've got a metal here. And then you've got a polyatomic ion. Okay. The metal is potassium, and that's in group 1A. And so any metal in group 1A is +1. So one of the elements is knocked out. We finished it right there just by looking at that. If it's in group 1A, it's +1. If it's in group 2A, it's +2. We don't have a rule for manganese, so we're going to have to leave that for now. We don't know what manganese is. But we do have a rule for oxygen. Oxygen is one of the 3 elements that are important here. And so oxygen is -2. So let me write oxygen is -2. So now, if you saw this problem on Alex, most likely what they're going to ask you for is not the oxidation state of every element. They're just going to want the manganese. That's the one they'll be interested in, because that's the one you have to kind of work through the whole thing to figure out. So here's how you go about it. You look at it, it has 0 charge, so that means it's a compound. Okay, so that means it's got to add up to 0. So here's what you do. You got potassium, which is +1. You got manganese, which you don't know. And you got 4 oxygens. And each oxygen is -2. So KMnO4, right? It's got to add up to 0. And then you just go through the arithmetic to figure out what it is. If you take 4 times -2, that's -8. -8 plus 1 over here on the left is -7, right? So you have Mn -7, right? All I did was I took this -8 and added to this, which is +1, and that gave me -7 on the left side. They have to add up to 0. So then to figure out what manganese is, you have to get the 7 to the other side. So you add 7 to both sides. And so now you get manganese on the left, and you get +7 on the right. And that's probably the highest oxidation state you'll ever see, is for manganese at +7. That's a very high oxidation state. And what that means is the manganese is very reactive. It has very powerful redox chemistry. The more extreme the numbers become, the more reactive the substances generally become. Okay. So if something is +1 or -1, it could still be reactive. But if it's +7 or +6 or -6, -5, this could be really reactive. Okay, so this is actually called potassium permanganate. It's a very famous reactant. So the potassium permanganate is the K plus, and then the permanganate is the MnO4 minus. So K plus MnO4 minus. Okay. So you can even do this with 3 elements. Okay. The last one, this one is tricky because it has 2 chromiums. So there's just a little more math involved. It's not really that more difficult. It's just there's an extra math step in there. So here's how we're going to deal with this one. The charge is -2. There are 2 chromiums. We don't know what chromium is, but we do know what oxygen is. And there are 7 oxygens. They have to add up to the charge. So they have to add up to -2. Okay. So how do we deal with this? Again, it's just an arithmetic. You got 2 chromiums. 7 times -2 is -14. And that's equal to -2. Again, we're trying to figure out what chromium is. We already know what oxygen is. We just looked it up. I mean, we just remembered it's going to be -2. So we got to get the 14 on the other side. So I'm going to add 14 to both sides. All right, if you add 14 to -14, you get 0. So that's going to be 0. And then you're going to have 2 chromiums. So just be careful. You have 2 chromiums here. And that's going to be equal to +12, right? 14 minus 2 is 12. So then we'd be careful. You might say, oh, chromium is 12, except that really the way this works is that 2 of the chromiums added together is 12. Together they're 12. So what do? You divide by 2. And so 2 divided by 2 is 1. So you get each chromium is +6. Again, this is very reactive. This is a dangerous form of chromium. If any of it gets into the drinking water, that creates a tremendous alarm and concern because chromium, it can cause all kinds of DNA problems because of its reactivity. So let me review this one. And there's a way to check. Here's what I'm going to do. All the oxidation states have to add up to the charge, which in this case is -2. So if chromium is +6, then that would mean 2 times +6, right? Here's your Cr2. And then oxygen's -2, so +2, 7 times -2. Just see if that equals -2, and it should, right? This is 12, this is -14. That equals -2. So that's just a little check. You don't have to do that step, but it just kind of checked that we got the right answer. Okay, so if you have 2 of the atoms, make sure you divide by 2 to figure out which each one was. So we don't report oxidation states like this. We wouldn't say Cr2 equals +12. We don't do it that way. We say each chromium is +6. Okay, and there you go. So practice those, and you'll get good at it. You'll get good at it pretty quickly. Let's see, I'm gonna take a look and see if there's any that they give you that are significantly different. Okay, KMNO4, CuCl2, those are all good. Oh, so there's one more type I want to show you. Very simple though. If you have just an element, not an ion, but an element. So for example, if it just says sodium, or if it just says hydrogen, or if it just says oxygen, or nitrogen. So those are elements, right? So if you look at it and there's only one element and there's no charges, they're equal to 0. So elements by definition have oxidation states of 0. That ends up being important when you start dealing with combustion reactions. So elements are 0. And then that's pretty much will get you through everything. Okay. Okay, let's see. Let's take a look at recognizing oxidation reduction. Okay. So let me create a new screen. So this is called recognizing reduction and oxidation. Okay, so in this particular problem, what they do is they give you, I'm going to leave the states of matter out. They're not important for solving these problems. They give you an equation, a chemical equation. And some of them are pretty complicated looking equations. They might have up to 3 reactants or 3 products. Generally, they're balanced. Okay, so they give you an equation there, and they will then highlight an element. So for this one, they highlight the phosphorus. So I'm going to highlight it by doing that. And then they want you to know whether it was oxidized, reduced, or neither, meaning it wasn't oxidized or reduced. So again, in chemical reactions, we have acid-base. Acid-base reactions do not necessarily have any changes in oxidation. They're not redox reactions, they're acid-base. Same with precipitation. A precipitation reaction is not necessarily a redox reaction. So to determine whether something is a redox reaction, you have to figure out whether the oxidation state changes. So here's how we deal with this. If the oxidation state increases, if it goes up, increases means more positive, then it's oxidized. Okay, so if the oxidation state of the phosphorus goes up, meaning it gets more positive, then we would say the phosphorus was oxidized. If the oxidation state decreases, in other words, it becomes less positive or more negative. Less positive is the same as more negative, right? So more negative, then it's reduced. Okay, and the reason for that is that something is reduced when it gains electrons. When the electron comes to it, it gets reduced. So if you're gaining electrons, you become more negative. If something is losing electrons, it's getting oxidized. So it becomes more positive because you're losing electrons, which are negatively charged, to become more positive. So for this one, they only want you to do one element. In this case, it's phosphorus. But if you take a look, what do you got to do? You got to go through and figure out what it is for both of them. So let's do the P4 first, and then we'll do the H3 Po4. Now, when you're doing this type of problem, don't worry about the coefficient. You can ignore the coefficient. This is just saying how many of the compound there is. So if you find out phosphorus is +3, and then there's 4 of the H3PO4s, all of them are +3, but we want to know how much 1 is. So you could ignore the coefficient. Okay, so let's do P4 first. That's easy. It's an element. Element is 0. So right there, we can indicate that the oxidation state is 0. Okay. Now the H3o Po4 is a little more complicated because we've got 3 elements in there. So what do? You first identify, is it a polyatomic ion? Is it a compound? There is no charge, so it must be a compound. That means they have to add up to 0, right? Everything in there has to add up to 0 if it's a compound. So we got 3 hydrogens. Hydrogen is +1. We have a phosphorus. We don't know what phosphorus is. That's what we're trying to find. And then we have 4 oxygens, and we know that oxygens are -2. It's a compound, so they got to add up to 0. Okay. So 3 times +3 is +3. 4 times -2 is -8. So 3 and -8 is -5. Add 5 to both sides, and you get phosphorus. Let me do it over here. Phosphorus equals +5. So over here is +5. And then you ask yourself, did it become more positive or did it become more negative? It went from 0 to +5. That's more positive, right? It's increasing. So the more positive it becomes, that would be oxidized. So the phosphorus in this case was oxidized. Okay. Now I'm not going to go through it with this one. They don't ask you to do it. However, if one reactant got oxidized, another one had to get reduced. And I won't go through it, but in fact, the oxygen got reduced. It started as 0 here because it's an element, and it ended as -2 over here. So it became more negative or less positive. So it actually got reduced. Okay. If you have something get oxidized, another thing has to get reduced. But they don't ask you to do that in this problem. So let's take a look at one more example here. The second example is CO. Oops. I wonder why. CO plus H2O becomes CO2 and H2. CO2 and H2. Oh, this is a way of forming hydrogen. Okay. That's cool. Hydrogen can be used as a fuel, so that's a nice little reaction to form a fuel. So here's, we have to figure out what element they want. They wanted in this particular problem, the hydrogen. Okay. So they wanted to know what happened with the hydrogen here. Okay. And again, the question is, did it get oxidized? Did it get reduced? Or neither? Okay, remember, oxidized more positive, reduced more negative, if it becomes more positive or if it becomes more negative. So we don't have to worry about this carbon here. That's not part of the problem. We don't have to worry about this oxygen. That's not part of it. So we don't even need to worry about these, right? They're not part of this problem at all. The hydrogen is what we're trying to figure out. So here's what we'll do. We'll do H2O first. And then we'll do H2. Okay. So that one's easy, right? Because we know that in a compound, hydrogen is +1, unless it's like H2O2, right? So we already know hydrogen is +1. Now over here, this is an element. Elements are 0, right? So that means the hydrogen went from +1 to 0. Sometimes I need to draw a little picture for myself just so that something becoming more positive or more negative. In this particular case, it's positive, now it's 0. So it's becoming less positive or more negative, right? That means the same thing. Less positive is the same as more negative. So it became less positive or more negative. So that's oxidized. I'm sorry. See, I made a mistake right there. Let me be a little bit more careful here. So more positive. So it became less positive and it became more negative. So that's reduced. Okay. Let me show you one more. And let's try this one. CuSO4 plus zinc goes to ZnSO4 plus Cu. Okay. In this particular one, we want to do the copper. Okay, so we're interested in the copper. So how do we deal with this one? First of all, we recognize this as a polyatomic ion. It's one of those polyatomic ions I talked about last week. Actually, at the beginning of this week, I think. The polyatomic ion is sulfate. And remember, sulfate is -2, right? Sulfate is -2. So what we do is we say, okay, you got copper sulfate. It's uncharged, so it's got to add up to 0. So the copper and the sulfate have to add up to 0. So if the sulfate is -2, that means the copper's got to be +2. Right? So really all you're doing with the ionic compounds in a sense are somewhat easy because you just have to remember what the negative charge is and then the positive's got to be the opposite of that. So that means copper's +2. Over here, the copper is an element. Elements are 0. So that means the copper is going from +2 over here to 0. So this is becoming less positive, or another way of putting it is it's becoming more negative. Less positive and more negative is reduction. So it's becoming reduced. Okay. As you do these problems, you might want to have a little flashcard next to you. And in the flashcard, maybe put, more positive equals oxidation or oxidized. And then less positive is equal to reduced. And then maybe have a second flashcard where you put, elements equals 0. Hydrogen is +1, oxygen is -2, fluorine is -1. Just put a few of those rules that I went over on those flashcards and just have them next to you when you're doing the problems. And then that should help you be able to get those. And then over time, you'll actually remember them. Okay. Let me show, I think we got enough time for maybe one more. Okay, so I'm going to try this one. It's called writing simple half reactions from the description. Okay, so they're actually going to give you the description. So they're going to give you the words and you have to kind of translate it into an equation again. So here it says write a balanced half reaction from aqueous iodide anions to gaseous diiodine. Okay, so be careful with your spelling here. It actually makes a difference in terms of how you interpret it. So here's what you're going to do. You look up, what is iodine? Iodine is I. It's iodide. So when it ends in IDE, you know it's negatively charged. Any substance that ends in IDE is negatively charged. So you look up, this is in group 7A. If it's in group 7A, it's -1. So you just put negative. It tells you it's aqueous. And then it says aqueous iodide anions, right? Negatively charged, converted into gaseous diiodine. Diiodine means I2. And then they tell you it's a gas. Okay. Remember, that's actually one of the 7 diatomic elements. They actually tell you diiodine to remind you. If it just said gaseous iodine, you'd put I2, but they reinforce it by saying it's diiodine to tell you it's diatomic. Okay. So here's what you do. First, you balance the equation. So you've got 2 iodines here, so you put a 2 on that side. Okay. Now here's the redox chemistry. This is called a half reaction. What you want to do is you want to add electrons. And we're going to use the symbol E negative to the more positive side to balance charge. You want to balance electrical charge by adding electrons to the more positive. Remember, electrons are negative, so if you add them to the more positive side, that will make it less positive. So I'm going to rewrite the equation just so we have room here. So remember, you first balance the number of atoms, and then you balance the charge. So this one's got a charge of -2. Because each one's negative, but there's 2 of them, so that's -2. This one over here has no charge at all, so it's 0. Okay, that means that they're unbalanced. They may be balanced in terms of atoms, but they're not balanced in terms of charge. The charge of the reactant side has to equal the charge of the product side. We can't create charge. So here's what we do. We add electrons to the more positive side. Why is this more positive? 0 is more positive than -2. So how many do we add? You just look at the difference in charge. That's a difference of 2, right? -2 is more negative by 2. So you put 2 electrons. And if the electrons are on the product side, that's oxidation. If the electrons are on the reactant side, then the reaction is reduction. So this is called a half reaction because it's half of a redox reaction. Redox is reduction and oxidation, both. If you're only showing one of the two, in this case oxidation, then it's a half of a redox. So we call it a half reaction. Okay, let me show you another example. Okay, in this one, they, again, same thing, write a balanced half reaction. So you can write a balanced half reaction. And then this is what they tell you have. They actually tell you it's reduction. Interesting, I didn't realize that. This one, they actually tell you it's reduction of aqueous iron 2 cat ions. Remember, cat means positive. 2 solid iron. Okay. So they're telling you what's turning into what. Okay. So iron, be careful. Iron is not IR. IR is iridium. It's a precious metal that we don't have very much of on the earth. Iron is Fe, ferrum. Okay. So it's reduction. So actually, since it's reduction, you know the electrons will be on the reactant side. So they're actually giving you a little hint there. But you're taking iron 2. Remember that Roman numeral is the charge. So it's telling you it's +2. So iron, Fe, charge is +2. It's aqueous. it's getting converted. Those are cations, positively charged. It's being converted into solid iron. So Fe. Solid iron, okay? So then, again, they tell you it's reduction, so you know the electrons will be on the left side, the reactant side. But even if they didn't tell you that, this is more positive, right? This is the more positive side because you've got +2 on the left side and you have 0 on the right side. Remember, an element is 0. So you add the electrons to the more positive side. So what's the difference in charge? 2. 0 and +2 are different by 2. So you add 2 electrons to the more positive side. And take a look at what happens. This is -2. This is +2. If you add those together, you get 0, right? -2 and +2 is 0, which is exactly the same charge that we have over here, 0. So you're adding the electrons to the side such that both sides have the equal charge. And in this case, it's reduction because it's on the reactant side. Okay. So some terminology there, right? Oxidation, reduction, oxidized, reduced. And then there's also reducing agent and oxidizing agents I mentioned at the beginning, okay? So that's pretty much it for section 4.4. There's one more section, which is called 4.5, and that one is molarity of solutions. It's actually called concentrations. Okay. So what I'm going to do is over the next, I guess maybe this weekend, I'm going to go ahead and just create a lecture for you on that section alone. And then I'll just post it to YouTube. We do have spring break coming up. And so the next assignment's not due till like a week after spring break. So I will go ahead and post a video. And then when we come back for the first meeting back, which I guess will be Tuesday, a week from this coming Tuesday, you can ask any questions on 4.5 that you want to. And then we'll start, I want to start working on the next topic, which is chapter 5. But I'll put a YouTube video for that one section. It should only be, I figure only a half hour, maybe 45 minutes. And you can watch it whenever you want to. Okay. So have a great break. It's Thursday, so I know you may still have class tomorrow, but have a great break. Reach out to me. I will still be around during spring break. So if you happen to be working on chemistry problems and stuff like that, you can reach out to me. I'll be around. And I'll post this. Okay. So be well, everybody. Take care, and I wish you the best.
Thank you, Professor.
Take care. Bye-bye.